The great Charles Sanders Peirce once said, "In no other branch of mathematics is it so easy to blunder as in probability theory." And ain't that the truth? Some of math's most infamously devious problems come from probability theory. The Monty Hall problem, the birthday paradox, the two children problem. Probability really has more tricky puzzles than you could shake a stick at. But suppose we have a stick, and it's broken at random into three pieces. Three pieces, of course, is just enough to make a triangle. But depending on the lengths of the pieces that result from the breaks, forming a triangle might not actually be possible. Then our question is, how likely is it? If a stick is broken at random into three pieces, what's the probability that the three pieces form a triangle? And indeed, this is another example of a devious probability puzzle. One of the things that makes this so tricky is that, as stated, the problem is pretty non-specific. I mean, yeah, we get the general idea, but exactly how is the stick going to be broken into the three pieces? Are we randomly selecting 2 points on the stick and making the cuts there? Or are we randomly selecting one cut and then randomly selecting one piece to randomly cut once more? You might not think it matters much. In either case, we're breaking the stick randomly into three pieces. Maybe it matters, maybe it doesn't. We'll answer that question later. But for now, we better darn well be sure about how we're breaking our stick. This stick-breaking problem originates from an 1854 Cambridge University exam. And in this original statement of the problem, it's pretty clear they're using the first method. A rod is marked at random at 2 points, and then divided into three parts at these points. So we're going to start by answering that question. When we randomly select 2 points on the stick to make cuts, what's the probability that the three pieces can form a triangle? Before we get into the details, I have to spend a long time on the internet to find things like old Cambridge exam papers, and it's critical that my data and computer are protected. For your security, look no further than today's video partner, NordVPN. Streaming, surfing, and reading emails all day presents a number of risks, so go to nordvpn.com/wrathofmath. NordVPN can recognize and protect you from malicious websites and links set up by scammers. With all the sites I use for research and downloading PDFs, NordVPN's Threat Protection Pro is a must. It scans my downloads to make sure that no malware puts a stop to my PDF hoarding. And when you're studying on public Wi-Fi, NordVPN is essential for encrypting your data so it isn't intercepted by cybercriminals. NordVPN helps when I'm streaming football games too, putting the kibosh on all those pop-up ads about grandmas in my area. Go to nordvpn.com/wrathofmath now and you can get a bonus 4 months with the purchase of a 2-year plan. Best of all, it's risk-free with NordVPN's 30-day money-back guarantee. Link in the description and pinned comment. That's nordvpn.com/wrathofmath. Your probability of staying safe online is strong with NordVPN. Now, let's talk about the probability of forming triangles from broken sticks. As we embark on this probability adventure together, one key thing to understand about probability is how useful geometry and area models can be in solving these sorts of problems. For example, what's the probability that in 2 coin flips, we get both a heads and a tails? If we say that this 1x1 unit square represents all the possibilities of 2 coin flips, clearly it has an area of 1, representing the 100% chance that something happens. And certainly, half of this square would be where our first flip is heads, and half would be where the first flip is tails. Then, in the heads rectangle, half of it is where the next flip is also heads, and half is where the next flip is tails. And in the tails rectangle, half of it is where the next flip is also tails, and half is where the next flip is heads. And thus, we see that half of the square is where we got both a heads and a tails. And so the answer to the question is 50%. For the stick problem, we'll also use an area model kind of like this. but a certain theorem from geometry is going to make a different shape the key to our solution. If the pieces that result from the breaks are A, B, and C, then certainly their sum has to equal the length of the stick. And let's agree for this whole discussion that the length of the stick is 1. The other key restriction is that if these pieces A, B, and C are going to form a triangle, no single piece can be too long. Obviously, if one of the broken pieces is too long, then the other two pieces may be unable to meet to form the triangle. And how long is too long? Well, perhaps not surprisingly, it's half the stick. If the piece A, for example, was longer than half the stick, then there's no way that B and C could meet to form a triangle, because even if we laid them down perfectly flat, together they're less than half the stick, and A is longer than that. So if any one piece is longer than half the stick, the other two pieces won't be able to bridge that distance to form a triangle, which gives us the last restriction that A, B, and C, all three of the piece lengths, must be less than a half. As long as these restrictions are met, then the pieces the stick is broken into will certainly be able to form a triangle. Now, for the coin flips, it was very easy to use a square as a model. That's because we already know the probabilities of coin flips, half heads, half tails, and it's easy to cut squares and rectangles in half. But for breaking a stick into 3 pieces and following these guidelines, a more clever model will be necessary, and a perfect model can be found in an equilateral triangle of height 1. If we randomly pick a point inside this equilateral triangle of height 1, its distances from the 3 sides have the very special property that they add to the height of the triangle. This fact is called Viviani's theorem, and it's easily proven. And to assist in the proof, here's a simple diagram from the Wikipedia page on the theorem. From the chosen point in the equilateral triangle, it's straightforward to join it to the 3 vertices, which then creates 3 interior triangles who have as their heights the distances between those triangles' sides and that chosen point. Clearly, those 3 triangles together form the entire triangle. And also, these 3 triangles have equal bases, since their bases are the sides of an equilateral triangle. Now, what's the area of the entire equilateral triangle? Well, let's say this is the base, and let's say it has length lowercase c, so then the area of the big equilateral triangle would be 1/2 times that base of c multiplied by whatever its height is. Again, we know that's equal to the added areas of these 3 smaller triangles. The area of this triangle would be 1/2 times the base of c times its height of s. The area of this triangle would be 1/2 times this base, which is the same as this base, so 1/2 times c times t, and this one, similarly, its area is 1/2 times c times u. So if we just take that factor of 1/2 and that base length of c out of each of those terms, the total area of these 3 triangles put together is 1/2 times c times s plus t plus u. We can cancel out the half c on both sides of the equation and establish Viviani's theorem. The height of the equilateral triangle is equal to the sum of the distances from the triangle's sides to a chosen interior point. So randomly picking a point in this equilateral triangle is equivalent to randomly breaking the stick at 2 points to form 3 pieces. By randomly picking a point in the triangle, we get these 3 distances, which we know add to the height of the triangle, which we've agreed is 1, which is also the length of our stick. And the distances that we get from picking a point in this equilateral triangle could take on any of the lengths that the pieces of our stick could, including pieces like these that do form triangles, and other distances that certainly do not. So we know all of the possibilities exist in this equilateral triangle model. Some of the possibilities do form triangles, some of them don't. So the question now is, what proportion of this space does contain points that correspond to piece lengths that can form triangles. Well, the piece lengths correspond to the distances between each side and the chosen point. And to form a triangle, we know that those distances cannot exceed 1/2. That means we can't get any further than 1/2 away from this side. We also can't get any further than 1/2 away from this side. And we can't get any further away than 1/2 from this side. Hence, the space of valid choices is this smaller equilateral triangle, which makes up exactly 1/4 of the whole space. Hence, if we randomly select 2 points on the stick to make cuts, the probability that the 3 pieces form a triangle is 1/4. If the randomly chosen point is in this central region, then the corresponding piece lengths will all be less than 1/2, so they'll be able to make a triangle. If the point lies anywhere else, then one of the sides is going to be prohibitively long. Now, how do things change, if at all, if we use the alternative method? If we randomly pick 1 point on the stick to cut, then randomly select one of the 2 pieces to randomly cut once more. Well, in this situation, after the first cut, if we randomly select the shorter of the 2 pieces to give a second cut, then we're certainly not going to be able to form a triangle, because the longer piece will be greater than half the stick and won't be cut again since we selected the shorter piece to receive the second cut. Now, you may also be wondering about the case where the first cut is exactly in the middle, so then neither piece is the shorter piece. Well, in this case, no matter what would happen next, our attempt to make a triangle would just look like a straight line, which is half the length of the stick. This is because one side would be half the stick, and the other 2 sides, no matter how they end up being split up, would perfectly coincide with half the stick. So it would give us a what's called degenerate triangle. And it doesn't actually matter whether we consider the degenerate case to be a triangle or not. It's only one edge case out of a continuum of others. So we'll just assume that there is a longer piece each time we cut the whole stick. So continuing our analysis of this situation, we know that half the time we'll end up selecting the shorter piece of the stick, and in those situations we'll not be able to form a triangle. When we randomly choose which piece to give the second cut, half of the time we will choose the longer piece though, and in that situation there is still hope. So let us again look at our equilateral triangle model. For the same reasons as before, this triangle in the middle represents the valid options for cuts that will allow us to form a triangle, because each point in this center triangle corresponds to pieces of our stick that are all less than 1/2. However, we're assuming that we've already made one cut, and we now have to perform another cut on the longer piece. Since we've already performed one cut, this entire triangle isn't available to us, because the length of the shorter piece is now fixed. And wherever our random second cut ends up putting us on this triangle, let's just agree that the vertical distance between this point and this side represents the length of the shorter piece that we're not cutting again. And if we agree to let that vertical distance represent the length of the shorter piece, then by definition of shorter in this situation, it certainly can't extend past this line. If the point were up here, then the length of the so-called shorter piece would be greater than 1/2, which would be a contradiction. After that first cut, the shorter piece can't possibly be more than half of the stick, only the longer piece can be. Then the situation is really just like before. All of the points in this central triangle represent valid options for cuts that would allow us to make a triangle with the pieces. However, less area is available to us because we can't have a point up here. So let's black that out. The length of the shorter piece can't be greater than 1/2, so this area isn't available to us. So what proportion of the available area represents a valid cut? Well, that would be 1 out of 3. So what are the odds that we'll be able to form a triangle if we cut using this second method? Like we said, after the first cut, there's a 1/2 chance we choose the shorter piece to cut again, and we will not be able to form a triangle in that situation. But the other half of the time, we choose the longer piece to give a second cut. And when we do that, there is a 1/3 possibility that the second cut will give us pieces with which we can form a triangle. And so the probability is 1/2 times 1/3, or 1/6. Isn't that surprising? This is how easy it is to make an error in probability. While randomly cutting a stick into 3 pieces may seem like a fairly simple procedure, this slight variation on how it's done results in a disparity greater than 8%. I mean, just imagine the scams you could pull with baloney like this. I could offer someone favorable odds to play this stick-breaking game, show them a convincing mathematical argument that the odds are as favorable as I claim, but then slightly adjust how the game actually works in a way that isn't noticeable to a layman, but as we've seen, it does meaningfully change the odds of the game. In fact, making a mistake in probability is so easy that not only do these 2 different ways of breaking the stick into 3 pieces produce 2 different probabilities, but this one isn't even correct. The erroneous explanation I gave for the 1/6 probability was also given by famous mathematics writer Martin Gardner. When he published an addendum to correct the error, he mentioned this mistake is found in many textbooks that discuss the problem. Even intelligent, diligent, and well-meaning sources can misstep when it comes to probability. Our area model worked in the first case because the possible cuts of the stick range uniformly over the equilateral triangle, so the area model accurately captures the random event. But in the sequential cutting method, the possible second cuts of the larger piece don't range uniformly over these 3 triangles, making this simple area model inaccurate. So let's address this sequential cutting method once more, but we're going to be more careful this time around. Again, we know the only way we're going to be able to form a triangle is if we choose the longer piece to give the second cut. That means the shorter piece is completely fixed. So then again, for the sake of a picture, we'll let the vertical distance of a point in this triangle represent the length of that fixed shorter stick piece. By the time we're making our second cut, the length of that shorter piece is completely fixed. So then the only points available in the triangle are points that have that vertical distance from the bottom side. Again, the idea of this one distance being fixed, we'll call it X, is that the shorter piece is not receiving the second cut. So the shorter piece has a fixed length, we're going to call that X. So as we go to make a second cut on the longer piece, the only points available in the triangle are those which are on this line, X units away from this side. Then, if the randomly chosen point is on this piece of the segment within the central triangle, that will be a favorable second cut, allowing us to form a triangle from the pieces. But if the point is over here, or over here, then we will not be able to form a triangle because one of the pieces will be too long. Then, to find the true probability, we need to find the ratio of this highlighted favorable part to this whole segment, and then add those ratios up for every possible length of x. And we can do that with an integral, where x, the length of the shorter piece, could be as small as 0 or as big as 1/2. Now, finding the ratio for any particular x of favorable outcomes to total possibilities is pretty easy to do. You've got to know that an equilateral triangle with a height of h has a side length of 2/√3 times that height. This yellow segment is actually the side of an equilateral triangle, this equilateral triangle here, which has a height of x, which means the side length of this equilateral triangle is 2/√3 times x. That's how long the good part of this segment is. How long is the entire thing? Well, this entire segment is also a side of an equilateral triangle, this one here. And its height, well, the entire thing has a height of 1. This part is a height of x. So this is 1 minus x. Hence, this whole side length would be 1 minus x times 2 over root 3. So this is over 1 minus x times 2 over root 3. Of course, the 2 over root 3's cancel out, and we see that the ratio we're going to need to integrate is x over 1 minus x. If you don't know how to do the calculus, don't worry, it's not hard. This is easily evaluated using a technique called U substitution or change of variable. And at the end of the day, it evaluates to -½ minus the natural log of 1/2. And that's approximately 0.193. So the true probability in this situation is a little bit bigger than we had thought. And again, that's 0.193, or about 19%, compared to the 25% chance using the first method of breaking the stick. With how frequently people have made mistakes on this problem, it just goes to show you can't be too careful when doing mathematics. But you know, one of the really nice things about a tricky problem becoming infamous is that many people will give it a try, and it's all but guaranteed that more interesting solutions and variations will emerge. Before we say sayonara, today, I'd like to show you a really elegant solution to the first variation of this problem, which was published by Andreas Lundblad about 1 decade ago in 2005. Wait. 1 decade ago was 2015. Andreas used a classic strategy in probability problems, which is to consider the opposite of what we're trying to calculate. The stick will be cut into 3 pieces, and if any of them are greater than 1/2, we won't be able to form a triangle. Now, when we randomly select 2 points on the stick to cut, what's the probability that, say, the leftmost piece is greater than 1/2? Well, certainly for the leftmost piece to be greater than 1/2, the 2 randomly chosen cuts need to be on the right half of the stick. And since we're just randomly choosing points on the stick, each cut has a 1/2 chance of being in the right half of the stick. We can thus multiply those together to find that there's a 1/4 chance that both of the random cuts are on the right half of the stick, making the leftmost piece greater than 1/2 in length. But of course, any of the pieces could end up being greater than 1/2, so the leftmost has a 4th chance of that happening. But what about the other pieces? Well, it turns out there's no meaningful difference between the leftmost piece and the other 2 pieces. To see why that is, imagine that the stick began as a circle, and we made 3 random cuts. The first cut only serves the purpose of letting us straighten out the stick. On the straightened out stick, let's represent that first cut right here. Then of course, when we make our 2 random cuts on the stick, we could just as well imagine them being made on the circle. And now you can see that there's no difference between the leftmost, middle, and rightmost piece, because by simply rotating the circle, any piece could play the role of the leftmost, or the middle, or the rightmost. The symmetry assures us that every piece has a 1/4 chance of being longer than 1/2. But of course, only one piece at a time could be longer than 1/2. That means there's no overlap between the situations where the left, middle, or right pieces are greater than 1/2. Hence, the total probability that any of the 3 pieces is greater than 1/2 can be found by just adding up those mutually exclusive probabilities that any one of the 3 pieces is greater than 1/2. Each piece has a 4th chance of exceeding 1/2, so in total it's 3/4, which leaves, as we already knew, a 1/4 probability left that none of the 3 pieces exceed 1/2, and so we would actually be able to form a triangle. What a cool solution. It really is the mark of a great problem that it has been studied and modified for over a century since the first known instance of it on that Cambridge exam. If you gave it a try before watching the solutions, let me know how it went and what your thought process was. And can you think of any other elegant solutions? Personally, I'm just glad this important lesson about care and diligence only cost us a few sticks. I guess I'd better go return these now.
Con mới ra đời, ba nghe ôm khẽ vào lòng, lặng nghe tiếng thì thầm hỡi bé cưng của ba. Con biết đi rồi. còn lớn hơn cả vĩ